Over the next few lessons, we're going to see where we can actually use series that we've been learning about. So if you've taken a statistics class, you've probably seen this picture below. We often call this a bell curve or a normal curve. And something we want to be able to do in statistics is find the area underneath the curve for a particular section. So an equation that gives us the normal curve is something in the form of e to the negative x squared. There might be some transformations or a constant, but generally e to the negative x squared would be a piece of our integral. If we're finding the area and we're integrating, it would be a piece of our integrand. So if we are trying to find the area under the curve using an integral, the problem is that this is not a formula that we know. We cannot integrate this with a u sub. We cannot integrate this with change of variable. There's none of the techniques that we've learned. We can't even use integration by parts here. So there's not a manipulation that we know. So because we can't integrate this, we have to have some other way that we can find the area under this curve. So since e to the negative x squared can't be integrated and doesn't have a formula, we have to use a different method. When I look at this graph, I can see that from 0 to 1, there clearly is an area under this curve. So we could also say that this function does not have a closed form antiderivative. So what that means is there's no formula for the antiderivative of e to the negative x squared that is in a closed form or that has a finite number of terms. So if it has a finite number of terms, it would be a closed antiderivative. So it turns out that what we're going to end up doing is we're going to find a series that models this function. And in order to start working through this process, what we're going to do is we're going to start by finding a polynomial that approximates this function. So we're going to find a polynomial that has this nice smooth curve to it. Because if we can find a polynomial that matches this exponential function, we would be able to do calculus on the polynomial, which is a lot easier than doing calculus on the exponentials or trigs or logs or anything like that. So the question is, how do we find a polynomial that approximates a function? In one way, and it's not the only way that we can do it, but one way that we could do this is called using a Taylor polynomial. So in CALCBC, we're going to look only at Taylor polynomials, and a Taylor polynomial is going to be a polynomial in the nth degree. So a Taylor polynomial could be like a second degree polynomial, a third degree polynomial. So when we look at the formula for finding a Taylor polynomial, it looks a little bit confusing at first, but it's really just a bunch of terms. So when I read this, this is the polynomial in the nth term of x. And if I look at each of these terms at a time, I notice that this first term, f of a, well, this is just our function f evaluated at some particular value a. Then we're adding to that f prime of a times x minus a to the first power. And if I look at this, just this first part of my Taylor polynomial, this is actually how we would write the equation for a tangent line. Like this piece of it, I'm going to erase this box in a second, but this piece of it is just the equation for a line in point slope form. All right, but as we keep going, so, oops. All right, well, won't let me erase. That's cool. All right, so as we keep looking at the polynomial, the next term, so our third term here, is the second derivative evaluated at a divided by 2 factorial times x minus a squared. Then my next term is, my fourth term is the third derivative evaluated at a divided by 3 factorial times x minus 3 cubed. And this goes on to the nth term. So like for example, if this is a 5th degree polynomial, this is going to go on until n is 5. So we would end up with like our fifth derivative evaluated at a divided by 5 factorial times x minus a to the fifth power. So again, if I look at the structure, there's a pattern here that would make this, that makes this easier to think about. So if I go back to my second term here, I could think of this as my first derivative divided by 1 factorial times x minus a to the first power. And I could even think of this as like my function value divided by 0 factorial, because remember 0 factorial is 1. And I could think of that times x minus a to the 0 power, which again would just be 1. So really each term of the polynomial, starting with like the 0th degree up to the nth degree, each term is the same. We just have to be really careful when we're finding it. So to get an idea for how this works, let's start with an easy function. F of x is the sine of x. And if we look at this first example, we're asked to find a first degree Taylor polynomial, a second degree, a third degree, and a fourth degree polynomial. So since f is just the sine of x, that means that f prime of x is just the cosine of x. So then my second derivative, f double prime of x, is going to be negative sine of x. I'm going to go ahead and take this out to the fourth derivative, since one of these will be a fourth degree polynomial. All right, so then my third derivative, f triple prime of x, that would just be negative cosine of x. And then my fourth derivative, remember we put a 4 there when we get past our third derivative, that would just be positive sine of x. All right, so if I'm looking to make my first degree Taylor polynomial, so my polynomial in the first degree, I'm going to need f evaluated at a. So our polynomial is going to be centered. We'll see in a second what that means. Centered at x equals pi over 6. So pi over 6 is my a value there. So my function sine of x at pi over 6 is just 1/2. So I need f of a, so the sine of pi over 6. And then to make this first degree, I'm going to have one more term. I'm going to use my first derivative. So plus f prime of a. So remember, f prime is the cosine of x. The cosine of pi over 6 is root 3 over 2. And that's going to be times x minus a. So x minus pi over 6 to the first power. So that is our first degree Taylor polynomial. All right, so if we make a second degree Taylor polynomial, it's going to start with those first two terms. So we still have f of a. So again, our function sine of x evaluated at pi over 6. So the sine of pi over 6 plus root 3 over 2 times x minus a, so x minus pi over 6. Again, that's to the first power. But now a second degree polynomial, we're going to go out to the second derivative. So our second derivative is the negative sine of x. So when I evaluate that for pi over 6, I have negative 1 times the sine of pi over 6. So that's a negative 1/2. So minus 1/2. But I have to divide that by 2 factorial. I'm just going to put it like that. So 1/2 divided by 2 factorial. And then I'll have x minus pi over 6 to the second power. So 1/2 divided by 2 factorial is the same as like 1/2 times 1 over 2 factorial. So if I clean this up, I really have 1/2 plus root 3 over 2 times x minus pi over 6 to the first power minus 1/4 times x minus pi over 6 to the second power. All right, so that's our second degree polynomial. So our third degree polynomial is going to start out with the first three terms that we just used. So 1/2 plus root 3 over 2 x minus pi over 6 to the first power. We don't have to write that exponent. Minus 1/4 x minus pi over 6 to the second power. And now we're going to add our third derivative. So our third derivative is negative cosine of x evaluated at pi over 6. So again, that's going to be a negative root 3 over 2. I'm going to erase this in a second. Divided by 3 factorial. So remember, 3 factorial is just 6. It's 3 times 2 times 1. I could think of it as 2 factorial times 3. So negative root 3 over 2 divided by 3 factorial is like multiplying by 1/6. So I should get negative root 3 over 12. So that was just 2 times 3 factorial on the bottom. And then this becomes x minus pi over 6 to the third power. So again, when we say a third degree polynomial, remember we stop when we get to the nth degree, so n is 3. So we stop when we're using our third derivative over here. All right, last one. We are also asked to find that fourth degree polynomial. So again, we start with all the same terms. We should have almost done the fourth one first and gone backwards. All right, so I'm up to my second degree here. This was, root 3 over 12 times x minus pi over 6 cubed. That's my third degree. And then when I get to my fourth degree, I need my fourth derivative, which is sine of x. I'm going to evaluate that at pi over 6. So the sine of pi over 6 is 1/2 again, but we now have to divide that by 4 factorial. And remember, if 3 factorial is 6, 4 factorial is 24. 3 factorial times 4. So this really becomes 1/48. And then I would have x minus pi over 6 to the fourth power. So I want to go back to this idea of where the Taylor polynomial is centered. And if we look at these graphs below, these are actually our polynomial graphs. So that first degree polynomial from that example, that is just the tangent line. So a first degree Taylor polynomial is a tangent line, and the point of tangency is where it's centered. So if I zoom in on this a little bit, my graph here is sine of x. And if I look at where this is centered, that's going to be our pi over 6. So this is centered at pi over 6. And this is, again, my first degree Taylor polynomial. So it's just a tangent line. All right, when we get to our second degree Taylor polynomial, it's like a tangent parabola. This is a quadratic approximation because our second degree Taylor polynomial had our tangent line minus a quadratic expression. So when I see what this looks like when I graph this polynomial, it's just a quadratic. So we could think of this as a quadratic approximation. Now notice that when we get close to where our second degree polynomial, we said it's again centered at pi over 6. Notice that now this polynomial is like closer to being this actual curve here. This is a better approximation for this area local to pi over 6 than the tangent line was. So when we get to our third degree polynomial, so this is our third degree polynomial, and again, we're centered each time at pi over 6. I notice that now the curve, this like cubic polynomial, is following this curve a little bit better. It's closer to being a better approximation when we are close to where our polynomial is centered at pi over 6. And then as I get to like this fourth degree polynomial, this was our fourth degree Taylor polynomial, I could see that it's really closely following the curve around pi over 6. So each polynomial, and you could see if we kept going, I would get like a 5th degree, then a 6th degree. As we keep going, each polynomial is going to get closer and closer and closer to matching this actual curve. So in general, the more terms that we use, the better our Taylor polynomial will do at approximating the function that we're working with. All right, so I want you to take a moment and see if you could try this next example. Find the third degree Taylor polynomial for g of x equals e to the x centered at x equals 1. Well, I know if I'm finding a third degree Taylor polynomial, I'm going to need my third derivative. So my first derivative is e to the x. My second derivative is e to the x. And my third derivative of g is e to the x. And I know that when I'm evaluating this at 1, g of 1 is just e to the first power, or just e. So all of my derivatives evaluated at 1 are just going to be e. So my third degree polynomial is going to be g of 1 plus g prime of 1 times x minus 1 to the first power plus my second derivative divided by 2 factorial times x minus 1 to the second power plus my third derivative divided by 3 factorial times x minus 1 to the third power. So we get e plus e times x minus 1 plus e over 2 times x minus 1 to the second power plus e over 6 times x minus 1 to the third power. And notice that each of those has a factor of e, so it's possible we could see this with the e factored out.